Hi ladies, this is lesson 10.4, and in this lesson we're going to look at the Pythagorean theorem, but if you remember back from earlier this semester, we talked a little bit about circles. We didn't do the whole unit on circles in chapter 9, so there's a couple little theorems that we're going to use, and I'll give you those as we were using them, but we have a few vocab terms that you need to remember from I think it was chapter 5. So those review vocab terms are tangent, inscribed angle, and semicircle. So we're just going to redefine those again for this lesson because again, this lesson deals with the Pythagorean theorem, but it also deals with how that can relate inside a circle. So the first term is tangent. So a tangent is a line that touches the outside of the circle at exactly one point. So it doesn't go through the circle, it just touches the outside of the circle. The second term is inscribed angle. An inscribed angle is an angle that's formed by two chords of a circle. So the chords of a circle go from one end of a circle to another end of the circle, not through any specific point, but an inscribed angle shares a common endpoint, which is the vertex of the angle. And then lastly, a semicircle. And a semicircle is half of a circle. And you form a semicircle by cutting the whole circle through the diameter. So a couple conjectures from chapter 9. Again, we did not do chapter 9, but a couple conjectures from the chapter is the tangent conjecture. And the tangent conjecture says that a tangent to a circle, so right here, this is our tangent. So a tangent to a circle is perpendicular to the radius drawn to the point of tangency. So this right here is the point of tangency. So from here to the radius, anywhere is this specific segment, the point of tangency, to the center of the circle, forms the radius. That is perpendicular. The radius is perpendicular to the tangent. Now, the second conjecture from chapter 9 that we're going to use in this lesson is that angles inscribed in a semicircle are right angles. So here is our semicircle. And we have an inscribed angle. So we have two chords of a semicircle that share a vertex. And those two chords that go from one end of the semicircle to the other end of the semicircle that share a vertex form right angles. All right, let's look at an example here dealing with the Pythagorean theorem and how they relate to circles. So looking at this circle, you can see that angle AMO is a right angle. So we can use the Pythagorean theorem to find that length, that radius of OA. So if OC is perpendicular to AB, and AB is 24 centimeters, and MC is 8 centimeters, we're looking for the diameter of the circle. So in order to find the diameter of the circle, it looks like we're going to be able to find the radius first because that's OC is the radius. And if we visualize a segment from O to A, that would also be the radius, and O to B would also be the radius. So let's look at how we're going to solve this problem. So we're going to look at it in several steps. So first, OA and OB are both radii of the circle. And they're congruent. All radii of a circle are the same length. So we know that these two are congruent, which makes triangle AOB an isosceles triangle. With an isosceles triangle, we know that the altitude of the isosceles triangle does a couple things. First, it bisects this angle. Secondly, it's perpendicular to the base. And third, it bisects the base. So if AB is 24 centimeters, then AM is half of 24 centimeters, which means that AM is 12 centimeters. All right, so now we know one side length of our isosceles triangle where the hypotenuse is the radius, and that's what we're looking for. We're looking for the radius so that we can find the diameter. Now the second part that we know is that MC is equal to 8 centimeters, and OC is the radius. Now we don't know what OM is, so we're just going to label that X. So if we label OM X, then we know that OC is X plus 8. And we also know that it's the radius. All right, then our next step, since we know that OA is the radius and OC is the radius and OB is the radius, then we know that OA is congruent to OC, and that's congruent to OB. So therefore, because this is X plus 8, we know that this is also X plus 8. OA is X plus 8 because it's the radius, and the radius is OC, which is X plus 8. So now on your note sheet, you just see that triangle outlined where X plus 8, that's the radius. We know that the base of this triangle is 12, and we know that the height of this triangle is X. We don't know what the value is, but we know in relation to the radius, where the radius is X plus 8, the height of this triangle is just X. We know that it's a right triangle, so we can use the Pythagorean theorem to solve this. So the Pythagorean theorem says 12 squared, one leg squared, plus the other leg squared, which is X squared, is equal to the hypotenuse squared. Our hypotenuse is X plus 8. So 12 squared is 144. X squared is just X squared. And then X plus 8 squared, remember you have to use FOIL for this. So 144 plus X squared equals X times X plus 8X plus 8X plus 64. So 144 plus X squared equals X squared plus 16X plus 64. Now we're going to subtract X squared from both sides in order to solve for X. So we have 144 equals 16X plus 64. Now we need to subtract 64 from both sides in order to solve for X. And we're left with 80 equals 16x. And then divide both sides by 16. And we get 5 equals x. Now the question is not to solve for x. That's going to help us, but that's not the question. The question is to find the diameter. So now we know a few more pieces. So we know that this is 12. We know that this is 5. We know that this is 8. And we know that this is x plus 8. So the hypotenuse of that triangle that we just solved for, we needed to solve for x first, but really what we're looking for is the radius. So the diameter is equal to 2 times the radius, where the radius is equal to 5 plus 8. So the radius is equal to 13. So if the diameter, that's what we're looking for, what's the diameter, is 2 times the radius. The diameter is equal to 2 times 13, which is 26 centimeters. All right, let's do this other example. And in this example, we're finding the area of that shaded region, and we're rounding our answer to the nearest tenth. So if you look at this diagram, we have to use that tangency conjecture that says a tangent to a circle is perpendicular to the radius. So here's our radius, and here's our tangent. So that is perpendicular. And the same is true here. This is perpendicular. So if you look right below step 1, because of the tangent conjecture, we have right angles formed from the tangent to the radius at the point of tangency. That gives us two 30, 60, 90 degree triangles because those two sides are congruent, and this is a 90 degree angle, and this whole angle is 120 degrees. So if those two sides are congruent, when we bisect that vertex, this would be a kite. When we draw the diagonal from the 120 degree angle to point H, that bisects both of those angles. So this angle is now 60 degrees. And since this is 90 degrees, these two angles have to both be 30 degrees. So we get two 30, 60, 90 degree triangles. So what we want to do is find the area of that segment. So first thing we're going to do is find the area of the two triangles. And then we're going to subtract the area of the unshaded sector. So this is a sector because this is the center of the circle. So first of all, our area of a triangle is equal to 1/2 base times height. We have two triangles. So we'll say area of triangle 1, area of triangle 2 is 1/2 base times height. And then the area of a sector is equal to the angle divided by 360 times pi r squared. So that was from chapter 8, the area of the sector. So before we can find the area of these triangles, all we really know is one of those side lengths. So we know the height In this triangle, we know that this is 8 times the square root of 3. We know that this is 60 degrees, and we know that this is 30 degrees, and it's a right triangle. So in a special right triangle, 30, 60, 90 degree right triangle, we know that 8 times the square root of 3 is also equal to the short side times the square root of 3. So that makes our short side 8. And we know the hypotenuse is 2a, which gives us 16, but we really don't need that piece of information for this problem. So there's one triangle. Now we have the second one, which is exactly the same. So this is 30 degrees. This is 60 degrees and 90 degrees. So the side opposite of our 60-degree triangle is 8 times the square root of 3. Our short side, side opposite of our 30-degree triangle, is 8. So if we're looking for the area of those two triangles, we have two triangles that both measure 1/2 base, which is 8, times height, which is 8 times the square root of 3. So to find the area of both of those triangles, we'll take 2 times 1/2 of 8, which is 4, times 8 times the square root of 3. And you don't really need these parentheses because multiplication is commutative, so it doesn't matter which order you do it in. So 8 times 8 times the square root of 3 is 64 times the square root of 3. Now it says that we can round our answer to the nearest tenth. So you can use your calculator to round 64 times the square root of 3. And that gives us approximately 110.85. If you're rounding to the nearest tenth, really that should be 110.9. All right, so that's the area of our triangles. Now we're not just looking for the area of the triangles, because if we found the area of the triangles, we would have this whole thing. But we're not looking for that whole area. We're only looking for the shaded area. So we need to subtract the area of that sector. So now let's find the area of the sector. And the area of a sector is the angle divided by 360 times pi r squared. So the angle is 120. We're dividing that by 360 times pi r squared. And in this example, we said r was 8. We know that our radius is from here to here. That was the short side of our 30, 60, 90 degree triangle. So that's how we know our radius is 8. So we want 1/3 times pi times 64. And again, we're rounding to the nearest tenth, so you can use your calculator. And that is approximately 67. So now we're going to take 110, that's the area of our two triangles, 0.9, and we're going to subtract the area of our sector, which is 67. And we get 43.9 centimeters squared for our area. All right, let's do one more example. In this example, we're finding the shaded area that's created by the circle that's circumscribed about the equilateral triangle. Okay, so a few things we know about this equilateral triangle. We know that it's equilateral, which means these are all equal, and any equilateral triangle is also an equiangular triangle. So we have to do two things. We're looking for the area of the circle. So we need to do two things. First, we know that the area of the circle is pi r squared, and we're looking for just the shaded region. So we need to subtract the area of the triangle, which is 1/2 base times height. Now, all we know is that the base is 2. We don't know what the height is. We don't know what the radius is. We know pi, and we know 1/2. But we need to find the height and we need to find the radius in order to solve this problem. So first, let's start by finding the height. So in order to find the height of this triangle, we first have to draw in the height. Since it's an equilateral triangle, we know that the altitude goes from the vertex to the midpoint of the opposite side. The altitude is also the median. And we know that it bisects this angle. So we know that that angle is 30 degrees. In an equilateral triangle, all angles are 60 degrees. So we know that we're working with a 30, 60, 90 degree triangle where the side opposite of the 30-degree angle is 1. So using our properties of equilateral triangles, we know that the hypotenuse of this triangle is 1 times the square root of 3, which is just the square root of 3. So now that we know height of the triangle, or now that we know the base of the triangle, actually the hypotenuse is not this, is not the square root of 3. That's the height of the triangle. That's the long side of the triangle. So now that we know the height, which is the square root of 3, we know that that's 2 because it's equilateral triangle. So since we know the height, we can find the area. So the area of this whole triangle is 1/2 times the base of the triangle, which is 2, times the height of the triangle, which is the square root of 3. So 1/2 of 2 is 1 times the square root of 3. That means our area is the square root of 3 centimeters squared. Okay, now we're not just looking for the area of the triangle, we also have to find the radius of this circle. So in order to find the radius of the circle, we're going to form another triangle. So again, the altitude of a triangle goes from the vertex to the midpoint of the opposite side. So we can draw in another altitude. So we already have this altitude, but we can draw in another altitude to help us form another triangle. So now we have just formed this triangle. And if you notice, this triangle includes the radius. It includes the radius in 2 spots. Here's one spot, and here's the other spot. Now I'm just going to erase the part that we already did so we don't have too many lines. So again, just labeling what we know. I'm drawing in 2 altitudes here. Okay, so I know that this angle is 30 degrees because an altitude bisects the vertex angle in an isosceles triangle. And I know that this angle is 30 degrees. Now looking at this triangle that I just drew, I know that this is the radius, and I know that this is the radius, but I don't know what the radius is. So since this is an isosceles triangle, that yellow triangle is isosceles, and the base angles are congruent, I know that to find the altitude of this triangle, it's going to form a right angle. Okay, so I'm just going to sketch this triangle over on the right. So here is the triangle I just drew, where this is 30 degrees, this is 90 degrees, there's the radius, but I don't know what my height is, but I do know that this is 1, because that whole side of the original equilateral triangle was 2, and the height or the altitude bisects that side length. So we know that this side is 1, this side is r. I know it's a 30, 60, 90 degree triangle. And I know that the side 1 is opposite of the 60 degree angle, which makes this the longer side. So if our shorter side is a, our longer side is a times the square root of 3. So in order to solve for a, I need to divide by the square root of 3, which means that a is equal to 1 over the square root of 3. Now that's not my radius, that's my short leg. My radius in this example is the hypotenuse, and the radius is equal to 2a, which means the radius is equal to 2 times the square root of 3. So my area of my circle is pi times my radius squared, which is equal to pi, and again, with our properties of exponents, is 4/3. So again, if we're looking for just the area of the shaded section, we're going to take 4/3 pi, and we're going to subtract the area of our triangle, which is the square root of 3. And if we're rounding our answer, which it asks you to, well, I don't know if it asks, but if you want to round your answer, round to the nearest tenth. So that's approximately 2.5 centimeters squared. And that's your final answer. So please jot down any questions you have from this lesson, and we can go over them when I see you in class. Thanks.